Alright, here's the answer portion of this ASE A6 Electrical Systems Simple Practice Test. And I'm probably going to do a couple more of these. You know, this is not going to be the only one. So I'm not putting a lot of schematics and stuff in here. Of course, you've already seen the test. But let's go on and get through this. Alright. The component not used in a brushed permanent magnet motor are the field coils. These are the field coils around the outside. And the field coils on these older starters are basically wired, it's wired in series. The commutator and the field coils are in series, so all the voltage going to the starter passes through the field coils and also passes through the armature, so that it can actually, you know, do its little magnetic chasing its tail thing. And so that's how that works. Alright, on a brushless permanent magnet motor, the permanent magnets are located on the rotor, and the electronics that drive the permanent, that drive that permanent magnet by working the magnetic field around the stator coils on the outside are actually, they actually are creating this magnetic field that, you know, spins that magnetic center. And that's the way it is with electric fuel pumps that are they're usually they'll typically have three phases, you know. Even though they're DC, they'll still have three phases. And some of your electric fuel pumps are like that now. They basically have those three windings going to them. And there's some electronics, even in a computer cooling fan. If you take a fan out of an old computer, those are DC brushless fans, and whenever you if you bust one of them apart, you'll find inside the hub of that fan a little circuit board, and it's basically got the necessary electronics to drive that brushless motor. So you can't have a brushless motor without some electronics. You know, the brushes basically reduce it to make it as simple as possible, and they have the windings around the thing and all that. But anyway, long and the short of it is that's how that works. Alright, question 3. Crank and current draw test on a cold 4-liter V6 engine shows 375 amp starter draw. Ambient temp 6 degrees, engine starts and runs normally. What's the most likely cause? Now, a loose alternator belt's not going to cause it to pull more amps. Wrong crankcase oil might be an element if it was too thick and it was winter time. That's why I put the ambient temp was 60 degrees, see. So you're basically not wanting any really thick oil in there. It's going to slow it down in the winter time. And a defective starter is the most likely cause for that. And, you know, there may be other causes you could come up with, but of these 4 choices, those are the ones. Which type of alternator stator has each phase winding connected to a common point? A Y-type stator is connected in the middle, and then the 3 legs coming out are what connects to the rectifier bridge, which are your diodes. The delta type stator, the ends of the windings are connected to each other, and those 3 junctions are what connects to your rectifier bridge. So it's not hard to remember that a Y-type stator, which is shaped like a Y whenever you look at it, is going to be connected in the center. Measuring available voltage to a component requires connecting the multimeter, excuse me, look at that, ooh, I screwed that wording up, didn't I? Sorry about that. Parallel with the load. Parallel with the load means you hook negative to negative and positive to positive. Now, if you're hooking it in series with the load to measure amps, you would basically have the current that's going, if you're using the amperage function on your meter, you would have it going through the meter on the way to the load. So you would disconnect one of the wires going to the load and hook the meter between the power source or between the ground and the wire that you disconnected from that. And so that's basically how you measure amps. Of course, on a meter that only, you know, the problem with meters is that people will forget and leave them set on amp measurement, and they'll leave the leads in the wrong hole, in the amp measuring holes, and then they'll forget and they'll connect the meter to the battery, and then they'll pop the fuse in the meter. And if you're using one of those fluke meters, you know, like so many people have, those fuses cost about $10 or $12 now. They're really expensive. Jerry Truglia, you know, ran a bunch of shops in New York, and he told me that somebody had given him a huge bag of those fuses, and one by one his technicians in his shops would blow those fuses until he had used all of those fuses up. But those fuses are really expensive, and so when I was teaching, I would get these little $10 meters that you know, that cost about as much as one of those fuses cost, and I would just buy like a bunch of them, you know, 10 or 12 of them. And if somebody stole one, or if they ran over it and crushed it or something like that, it didn't matter, because it only cost $10 anyway. And those meters would do whatever they needed to do, plus the student had to find whatever reading they wanted. Now, the other part of that about it is, if you're trying to learn to read a meter and you used one where you had to select the range, and you're using an auto ranging meter, you might get in trouble trying to figure out what that reading is if you don't pay attention to the little symbol, whether it's ohms or kilo ohms or mega ohms or whatever. That's another story. All right. When testing the integrity of a load ground, you should always use a headlight bulb. For years and years and years, I would hear these people who had been trained to teach at, you know, factory schools and all saying, never use a test light anymore. Throw your test light away. Always use a digital meter or you'll burn up the computer. And somebody somewhere may have burned up a computer using a test light to test the wrong thing. But anybody that even halfway knows what they're doing knows when to use a test light and when to use a meter. But if you've got a load-bearing ground that's made to pull, I mean, it's got to pull a load, it's got to be able to carry some current, you're not going to be able to do anything with a meter, and a lot of times even a test light, which only pulls about 1/4 of an amp, even if it's low impedance. That doesn't help you at all in a situation. One time I was working on a car with anti-lock brakes, and it was throwing me a code, and I went all the way through the trouble tree, and at one point it said measure this voltage at this relay, you know, the output voltage from the relay, and if it's over 10 volts then go to the next step. And it turned out at the end of the day that yes, it was measuring 11 volts, but when I tried to check that voltage, and it was a good strong feed with my test light, that voltage would go away because there was enough voltage drop on the little contacts in that relay that it just wasn't sending any juice through there. And that was infuriating to me, and I got to the point to where I only use digital voltometers to read stuff like reference voltage and that kind of thing. But if it's carrying any kind of a load, fuel pump, fan motor, whatever, and it's not working, you better be checking that ground with something that'll pull 4 or 5 amps, or as close as you can to the amount of amperage that thing pulls, which a headlight bulb pulls at. Some of the schools, you know, like at KC Vision and places like that, if you see these electrical classes, they'll tell you to build a box with 6 tail light bulbs in it. And they'll basically tell you that they do that so that if you need less of a load, you can take some of the bulbs out or whatever. But you want to be able to tell if it's burning that headlight dim, but it's actually burning your test light bright. I've got a video on my channel that you might want to look up that says when a meter and a test light aren't enough. And we had a fuel pump situation where the fuel pump wouldn't run, and I checked it unplugged it and checked with a test light, and the light came on. I said, well, it must be something wrong with the fuel pump. So I pulled it out, put it on the bench, hooked it up to independent power, and it ran. I said, well, it ain't the pump. So I put it back in. Then I got the headlight bulb, and I tested it with that. That current would not burn a headlight bulb. And I had voltage drop in a ground circuit on that pump, so I ran a separate ground, which is all you need to do a lot of the time. And I grounded the pump, and then the engine started to run. But one way or another, you needed something that will pull some current if you're measuring a load-bearing circuit. A digital voltometer is used for open circuit voltage testing. That's what I was referring to just now. That's my meter. I bought that meter for like $350. My gosh, back in the 90s from the Mac tool guy. It's made by Tektronix, but it's an ET332. And that thing will check injector pulse and all kinds of cool stuff. I really got a lot of good use out of that meter, but it's got one of those $10 or $12 fuses in it, and I had to be really careful about that. The circuit shown is a parallel circuit because you got 3 of them that are hooked between A and B. The resistance reading between A and B will be approximately 0.6 ohms. And the reason I'm saying that is because it's always going to be less than the least, because each one of these represents another place current can flow. And so the total resistance of the circuit measured from A to B is going to be less than this, because these provide a little additional current flow. And so anytime you see a question like this, it's always going to be less than the least. Just always remember that, because on a parallel circuit, you don't add the things. You basically have to, there's a formula for it that I'm not going to go into right now. I could have, but I didn't want to use a lot of time on that. That's for another time. Alright, when a component is drawn with dashed or dotted lines like that right there, that means there's parts of the component that aren't shown. Alright? And so that's what that means. When tracing a short or an open, a smart technician will check which points first. Now, you might be a sequential person like me and you feel like I want to follow this from the fuse panel all the way down the circuit to the component and then keep going that way. But the smartest thing you can do is find the easiest connector to get to, and you can get an idea which side of that connector the problem is on if you do your testing the right way. So you check at the easiest. If there's a connector right on top of the engine that you can get to and find out which side of the circuit this is on, then there's no need in ripping half the dash apart to get to the wires coming off the ignition switch. You understand what I'm saying? So basically, if you go to the easiest place first, then that's the way that works. I had a parts man one time, a new parts guy, but he was very experienced. He came to the dealership where I was working, and I remember going into that parts room one day, and there was another mechanic and a parts man that had been there longer. And that's back when everybody was looking stuff up on microfiche. We didn't have computers. This is a long time ago. And I went in there and I said, I walked up to the parts guy that was very experienced but new, and I said, James, I need an air horn gasket for an Escort carburetor. And so before he could even say anything, this mechanic and this other parts guy were saying, you got to have a carburetor number, you got to have a carburetor number, la 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 la. And they went on and on for a little bit, and then when they finally shut up, he just looked back at me and said, what year model is it? And I said, it's an 83 model. And so he went back there and he got one off the shelf and threw it on the counter. And I said later, when they weren't within earshot, I said, why does Lewis always have to look the part up every single time and you just threw it on the counter? I don't understand that. He says, there's only two. He said, I'm lazy. There's only two. I noted when the breakover was. If it's newer than an 82, it's going to have this air horn gasket you wanted. If it's older, if it's an 82 or an 81, it's going to have the older gasket. So the carburetor changed in 83, and he said, and I just happened to commit that to memory. That's a good parts guy whenever you got somebody like that. But the point is, the easiest accessible. Sometimes it's good to be a little bit lazy if it gets the job done quicker and efficiently and you're accurate in your diagnosis. But you can work your rear end off doing work that you didn't need to do because you're trying to be too sequential. That was the deal on that. Measured resistance of a disconnected tail lamp bulb line on the bench is found to be 2 ohms. With the bulb connected and power flowing, the calculated resistance is 6 ohms when you use the EIR formula. The bulb is positive temperature coefficient. When current is flowing through that bulb, it has more resistance than when you're measuring it with a meter, because the meter is not putting a load on the bulb. And the current, you cannot directly measure the ohms of that element while it's burning, but you can calculate it if you use the EIR. You know, if you multiply this times this, you're going to get that. If you divide that into that, you're going to get that, and so on and so forth, and divide that. See, this is current or amps. This is resistance, and that's E would be your voltage. So basically, if you had your current and your voltage, you can calculate resistance. Now, something that's not included on this, if you multiply that times that, that puts another thing out here. That gives you your watts. So anyway, but just I won't charge you any extra for that information. All right, 3-minute charge on a high session. The voltage reading for a 12-volt battery is 17.5 volts. The battery is sulfated. You can check for a sulfated battery very good if you've got it. Now, the trickle chargers, it's going to have to charge a lot longer, but if you've got a high charge, fast battery charger, you can hook that up to the battery, have your meter already connected, read that battery voltage, hook it up, walk away for about 3 minutes, comeback, if that thing has drifted up over 15.5 volts, or if it ever does when you're charging it with any charger, and I'm not talking about the alternator because that's different, because there can be problems with the alternator that can push the charging system voltage too high, you know, if there's something wrong with it, because the alternator is a lot stronger about that if it's full fielded, you know, and you're spinning it really fast. But a battery charger, within 3 minutes, if it goes above 15.5 volts, then you can pretty much say that battery sulfated, and that's a really good test. A waveform displayed on a lab scope is voltage over time. So this is time, this is voltage. This right here, this little right here, they call that a gradicle. And whenever you're setting your meter up, each one of these divisions, you know, whenever you see it set up for so many milliseconds, that's so many milliseconds per division. All right, this right here is how many volts per division. So if you've got it set on 2 volts, that means it's going to be 2, 4, 6, 8, 10, 12. You know, see what I'm saying? And if you got it set on like 500 milliseconds, then it's, you know, 500, 500, 500, 500. So you got to kind of understand that too. But that's a voltage over time thing. Higher than normal current flow in a circuit could be caused by a short circuit. Poor connections are not going to cause higher current flow. An undersized wire is not going to cause it. A burned out light bulb is not going to cause it. So a short circuit's about the only good answer there. Each cell in a healthy automotive battery produces 2.1 volts, and there is a way you can actually measure the voltage in each cell. I've already talked about that on some of these videos, but I'll cover it again later. The red brake light comes on when the key's in start, that's the prove out, and remains on for the first 2 miles of driving before it goes off. That's low brake fluid. The brake fluid heats up and swells up and raises a little float, and then the light goes off. That's common because the brake fluid level goes down as the disc pads wear, and that fluid goes into those calipers. And so it's not unusual to have to add some fluid over the life of the brake pads because it's going to go low. And it'll get to the point to where you'll see that light right there. Which sensor creates its own voltage signal? Oxygen sensors got ceramic zirconia, the conventional one does. And that ceramic zirconia actually creates voltage. It compares the air in the atmosphere to what's in the exhaust, and that ceramic zirconia is an electrolyte, and it basically creates that voltage, and it happens really, really fast. You know, you might have remembered I had this video where I had a piece of a converter here where you had it that was cut off. It was like a converter shell and had an oxygen sensor screwed in there, and it had it hooked to an oscilloscope, and we were using a bottle torch. And when the bottle torch will heat that thing up to that 600 degrees, where it'll start working, and you can watch that. You can test an oxygen sensor by using a bottle torch, and when you get it to where that voltage goes up, you can move that bottle torch back and forth, and that thing will instantly respond to that. So that's another little test there. Customer says the dash lights look at that. I can't believe I screwed that one up. To illuminate when the brakes are applied. This is most likely a bad stoplight bulb. I saw this several times. The 2 filaments in the bulb would short out with one another. And whenever somebody would mash the brake, they'd see that, you know, and over time when those bulbs are burning, those wires can change, you know, the ones that are next to each other that are going up. This is more common on the bulbs with the brass bottom than it is on the bulbs like the, you know, that just have the little plastic bottom and the wires that plug in and all that. So anyway, this one here is a bad stoplight bulb. That's what that is. And here's the other thing. If you've got a problem where the instrument cluster lights are popping on, because see, they're on the same circuit with the tail lights. So when the stoplights come on, they backfeed from the tail light circuit into the instrument cluster, and it, you know, lights up the illumination because there's a separate fuse for illumination, but it's basically hooked into that tail light circuit typically. Now, newer vehicles, body computers, you know, this doesn't apply to them, and there's all kinds of crazy stuff going on with the electronics and the way the lights are set up nowadays. You know, some of them will basically have lights that are fed with power, and the modules will feed ground to the lights. First time I saw that was on an Eagle Premier back in 1988. The bulbs were hardwired to power, and this lighting control module would send ground to the light. You know. All right, question 20. All 3 wires on a TP sensor are reading 5 volts. That means the signal return wire, which is the ground going back to the computer, if you want to horse around with that on one that that belongs to you or something you're trying to experiment with, if you snip or maybe unkey that signal return wire and disengage it, then the wire, well, you'd have to snip it for all three wires. So you snip the signal return wire, all three of those wires are going to read 5 volts. The signal wire going to the PCM, the voltage reference wire, which is where that's coming from the PCM, and the signal return wire coming out of the sensor. That typically means the wire is cut, but the signal return wire, which would be the ground, is cut between the sensor and the engine controller. And so that's what you're going to run into right there. Of course, if the signal return wire is shorted to ground, it won't matter. If it's shorted to the signal wire, it will pull it to ground. If it's shorted to the VREF wire, on a Ford it probably won't start. On a GM it will, because they've got more than one reference voltage feed going to various sensors and all. Anyway, I keep popping this slide up with this guy and this big dog. That's a sort of an error, but don't pay any attention to that. And there's my little coffee pot and my meter and my wrenches. So anyway, I just wanted to run through one of these tests, and I hope you guys get some good out of this. And I will do another A6 test very soon. So I'll talk to you guys later.